Let's look at the question. Find all numbers disappeared in an array. We are given array names of an integer, while names at I is in the range of 1 to n, and we need to return an array of all integers in the range from 1 to n that do not appear in the names. So if you decide to use additional memory, then this is a really easy problem, right? Actually, using counters and store them into our additional memory, it is a good idea for us to write an initial solution. The intuition behind is using a hash map. It is pretty clear that in this case, we are given that array would be the size of n, and it should be contain numbers from 1 to n. However, some of the numbers are missing. All we have to do is keep track of which numbers we are encountered in this array, and then iterate from 1 to n and check which numbers didn't appear in this hash map. Those didn't appear numbers would be our missing numbers. So based on this idea, let's look at a more formal algorithm. We will use a hash table for keep track of the numbers in this array. First, we initialize a hash map. The hash is used to keep track of the numbers that we encounter in this array. We can use a set data structure as well in this case, since we are not concerned about the frequencies account of the element. We have used a hash mapper of size of 9. They have ordered, so the keys of the hash map is from 0 to 8. We will also use a simple hash function that will directly map the array entries to the corresponding keys in the hash map. Usually, the mapping is not that simple, and it depends upon the hash function being used in the implementation of the hash map. So next, we can iterate over the given array of the one element at a time, and for each element, we just add each of number to the hash table. That means just insert an entry in the hash map. And for number that was already present in the hash map, we will mark it with a value 1 so that we can see the duplicate element easily in the end. Even if an entry will exist before in the hash map, it will simply be overwritten. Once we process the last element of the array, let's look at the final state of the hash map. We know the unique set of elements from the array. We can simply find out and iterate all the numbers from 1 to 0, and for each number, we just check if it is an entry in the hash map. If there is no entry, we just add the missing number into the result array. The missing element is from the range 1 to n. So response array that would contain the missing number and add those who don't appear in the hash map that will return from the function eventually. Let's try to implement the algorithm in the Python. As we can show, we can have an input example here. We have to first create a hash table. Hash table is a set. And then we use a for loop to iterate over number in the input array lambs for num in lambs. And so every hash table will write a number inside it from the 0 to here. So we can print a result to show how it works. Yeah, so it will automatically write every element inside here except the duplicate element will automatically overwritten, and we can have a new array. This array will hold the missing number, and we can loop again to find a missing number for num in range. This time we loop from index 1 to the length of the lambs. So and plus 1. So from the 1 to the length of names, and if name is not in the hash table, we just add it inside it, right? Append the name inside it, and we can print them out. Now we can return. So first we print them out. The result, yeah, it's 7 and 8, and to build a function we have to return result, and to build a function, to define function, define find disappeared numbers self names, and class solution. Then print them out. Print this one. Print solution dot find. Wait a minute. Indentation. Oh, we forget the indentation. Yeah, it works. It's 7 and 8. As the question asks us, can we do it without extra space and in O of n runtime? You may assume the return list does not count as extra space. However, the trick really is to not use any additional space than what is really available to use. Sometimes multiple passes over the input array will help us find the solution. There is an interesting piece of information in this program that will make it easy to reuse the input array itself for this solution. The program specifies that the numbers in this array will be the range from 1 to n, where n is the number of the elements in the array. Can we use this information and modify the array in place somehow to find what we need? We definitely need to keep track of all the unique number that appears in this array. However, we don't want to use any extra space for it. This solution that we are looking at in just a moment springs from the fact that all elements are in the range from 1 to n. Since we are given this information, we can make use of the input array itself to somehow mark the visitor numbers and then find our missing number. Now, we don't want to change the actual data in the array, but who is stopping us from changing the magnitude of the numbers in this array? That's the basic idea behind this algorithm. We will be first negating the numbers seen in this array and use the sign of each of the numbers to find our missing elements. We will be first treating numbers in this array as indices and marking corresponding locations in this array as negative. The algorithm is like that. In the input original array, we iterate over each of the elements at a time, treat the value as a new index, and check the magnitude of the value at the new index. So if the magnitude is positive, we will make it to negative. Specifically, for each element names at I, if it is not already marked, we will mark the element negative at the corresponding location. For example, it's like names at I -1 magnitude the -1. Thus, we indicating that the numbers names at I has been appeared or has been visited. Now, we loop over the numbers from 1 to n. For each number, check if it is a names j is a negative. If it is a negative, that means we have seen this number somewhere in this array. Add all the numbers to the resultant array, which don't have their corresponding location, will be marked as a negative in this original array. And we iterate over the numbers from 1 to n and add all of these that have a positive magnitude in this array. So this is how we respond to the array that could contain the missing numbers. So the time complexity is O of n because we have used 2 for loop, and the space complexity is O of 1 since we are reusing the input array itself as a hash tuple, and the space occupied by the output array that doesn't come to the space complexity of the algorithm. Let's try to turn the algorithm into Python. First, we have this example is an input array, and we need to create an empty list. Is our result. It's an empty list, and before that, we need to process the number, the number we visited. For I in range, the range is the boundary is the length of the lambs. And we declare a new variable, new index. Is absolute. We use absolute because we will turn it to a negative. Names at I is -1 because the index is less than the number. All right, start from 0. And if names at the new index is bigger than 0, that means we are already this is our first time meet them. So first time meet them, we need to turn them into a negative number. We multiply by a -1 to turn them into a negative number. So we can print them out to see the result. We meet the first. We meet the first 6 elements and turn them into a negative number, and then we can add the positive one into our empty list. For I in range 1 to the length lambs. So this is everything is +1 because we use the index. If the lambs I -1 is bigger than 0, that means we meet them before. We just append them to the index to our empty list, and then we can print them out, print our result. Yeah, it's 7 and 8 is the last 2. Then we can remove this and return the result in the class solution. Define find disappeared numbers, self numbers, and get an indentation and print a solution dot find. Yeah, is 7 and 8.